Hello, welcome back. We've been talking about light. Today we're going to talk about how it can cross a wide spectrum of different types of light. Not just the visible light that we're most familiar with, but things like X-rays, microwaves, radio waves. All of these sort of things fall under the heading of light. They're all part of the electromagnetic spectrum. So this is 6.3, the electromagnetic spectrum. The frequency of the light determines its energy level and many of its characteristics. Frequency is how many waves occur per second. It's measured in hertz, which can be abbreviated just Hz. So down here we have a diagram showing the electromagnetic spectrum. There you go. This is the way that travels for increasing frequency. It also has increasing energy towards the left here. As we increase the frequency, the waves get tighter together. That's why they have higher waves per second. They're moving more quickly together. As we move down the frequency, the waves get spread out further and further apart. This means that they have increasing wavelength as we move down. Wavelength works in the opposite direction than frequency. As the frequency goes up, the wavelength goes down. And here it's got some sizes, nanometers and more nanometers, centimeters, 1 centimeter, 1 meter, 100 meters across. Wow, the wavelengths can get extremely long, even kilometers or even light years long. There's not really an end other than the size of the universe. At the very, very small end, where the wavelengths are very small and the frequency is very high, we have gamma rays. Those are the highest energy form. Below that, we have X-rays, which are used to take pictures of our bones and stuff. Below that, less energy, is ultraviolet light. This can give us sunburn and stuff like that, so it's still got plenty of energy and can be very damaging. And then here's our visible light spectrum. It's this tiny, narrow little band. The part of the electromagnetic spectrum that we can actually see is very, very small. Some organisms can see more. Some snakes and stuff can see into the infrared, and there's some insects that can see in ultraviolet. The humans only have this narrow little band. And down here, they just pulled that tiny little section out and widened it so we can kind of see. This is where all the different colors of light fall. We can see from about 400 nanometer wavelength to 700 nanometers. And that's everything we see, the entire rainbow. With less energy than that is infrared. This is usually felt as heat. We have infrared sensors and infrared cameras and stuff like that, but we can't see it ourselves. And then anything that's lower energy than that, oh, this is missing. There should be microwaves in here. Microwaves and then radio waves. So down here, we're just going to go through each of these different areas one at a time and talk about their uses. So, starting with the lowest energy. Radio waves have the longest wavelengths and the shortest frequencies. As you might expect, they're used for radios, for hearing the music we like to listen to in the car, but they're also used for a lot of other things as well. TV signals travel through radio waves, communication satellites use them, radar uses it. We actually have an entire government division that is maybe it's FCA. I remember, but their job basically is to make sure that there's not a lot of overlap and what people are using these different sections for. Because if there was, there'd be lots and lots of interference. And so, like one radio station, 98.9 or whatever, has to rent basically just one tiny little area of the radio wave spectrum, and that's the only place they're allowed to put their stuff. If they leak over into other people's stuff, they'll get fined. So it's all under control from the government just to prevent a lot of people using the same areas and causing interference with one another. Okay, microwaves. Microwaves are probably most famous when we use them to cook our food, but that's actually a very specifically targeted range of microwaves, where it's targeting water molecules and causing the water molecules to vibrate, and this is why foods that are very, very dry, for example, don't heat up as well compared to wet foods. But if you use other parts of the microwave spectrum that don't target water molecules, you can use it for Wi-Fi, for our cell phone signals, even for a form of radar. Then infrared, we can sense it as heat. We can use it for cooking through our infrared ovens. And we also use it for like night vision goggles or infrared cameras. Some snakes and reptiles and some insects can also see or sense infrared. We don't know whether it's necessarily like vision with their eyes. Sometimes they have the infrared sensors on their bodies as pets or whatever. So we don't really know how they integrate that. Maybe it's more like a sense of smell, like a direction, or maybe they can actually see it. I don't know. But it gives them a way to to get information about the world around them that way. All right, then visible light, the wavelengths that are wavelengths that are detected by the retinas of our eyes. Very narrow range, like I said, 400 to 700 nanometers. It's significant to us because we use it to see, but it doesn't really have much significance compared to the rest of the electromagnetic spectrum. But this is the part that most easily penetrates Earth's atmosphere, and so most of the sun's light that falls in this range actually reaches the surface, and so that's probably why we use this particular band, because it's just the most widely available light that actually hits the surface. Mostly like the ultraviolet and the infrared is absorbed by the atmosphere and doesn't get all the way down here. And the higher energy ones would be too dangerous anyway because they can damage our cells. Alright, ultraviolet light then has higher energy than visible light. We can use it to sterilize equipment because it kills bacteria. It can be seen by some insects. If you look at like flowers and stuff like that in ultraviolet, they actually have some patterns, spots and lines and stuff like that insects can see that we can't, to help direct the insects to the nectar and pollen. It is higher energy though, because it causes sunburns and can damage DNA, leading to skin cancer, but we do use it ourselves as part of a metabolic process to make vitamin D in our skin. And if you don't have enough vitamin D, you get a disease called rickets, which makes your bones go kind of soft and squishy. So nowadays that we stay inside so much, we often add vitamin D to other foods, like on milk you can buy vitamin D milk. And then X-rays, these are higher energy. They can penetrate more deeply into some materials. We use them to visualize bones and internal organs. Too much exposure can lead to damage to our DNA and cancers though as well. And then finally the highest energy with the gamma rays. These are extremely high energy and very, very dangerous. This causes so much DNA damage that it basically shuts down your genetic material and you would die from the damage. You can't replicate your cells anymore. And so you start having problems with the tissues that slough off their cells the fastest, and it's very, very unpleasant. But it can be used medically, though, because you can target the beams very narrowly, and then if you just treat the cancer with them, cancer divide very rapidly, and so by damaging the DNA of the cancer cells, it'll die off more quickly compared to the surrounding cells. But you do have to be very, very careful with it, as you might expect. Anyway, that's the end of the notes. Hopefully that was a good overview of our electromagnetic spectrum. You'll be doing a worksheet with a slightly different version of this diagram and answering questions about from that diagram. So hopefully it'll make sense. Thank you and have a great day.